Okay, I've got quite a long question about rice. Packets, the manufacturer claims contain a mean of more than 250 grams. So there's a claimed population mean, and then we're assuming that the weight of packets are normally distributed, and a sample is collected, and we've got an X bar value. There are 50 packets, and we've got this statistic here. So I'm going to need to get a value for S, okay, which is well, S squared, it says, is an unbiased estimate of the population variance. So in other words, with S, we're trying to estimate the population standard deviation. So we just use our standard recipe for estimating the standard deviation. So we use our SX formula. Okay, we haven't got the raw data, so we can't enter it into our calculator. So this is the formula from near the beginning of the S1 module that you need to have remembered, which is that Sx is x minus x bar in a brackets squared all over n minus 1. In fact, I need the square root of all of that. So using the values from the question, I need the square root of the x minus x bar squared, which is 184.5, and n minus 1, there were 50 packets, that was my n, so I divide by 49. So when I do that on my calculator, notice I've got the square root going over everything. You may find it more convenient to calculate this fraction and then square root the answer. Anyhow, if I do that properly, then I get the answer of 1.94. Now, because the answer is given, 1.94, I want to be convincing that I've got this myself. So I'm going to say 1.94. I'm going to write down 0.44. And then I'm going to say round to 1.94 to 3 significant figures. So if they give you a numerical value, then get it to more precision than it's given to first, and then show it rounds to what it's supposed to. So we've got Sx, which is an estimate of our population standard deviation. Now we've got to get a 96%, slightly unusual percentage there, 96% confidence interval for the mean weight of rice in a packet. So my confidence interval recipe, which you learn, is x bar plus or minus a z value times the standard error sigma over root n. So I need a value of sigma. Well, that's what I just estimated. I've got an estimate of the standard deviation. So I'm going to be taking sigma is 1.94. That's the best I can do for an estimate. I've got obviously an n value. N was the number of items in the sample, so n is 50. I've got an x bar, okay, or at least I need an x bar, and that's given us 251.1. So x bar is 251.1. So all that's left is my z value. Now z value comes from the percentage of confidence, so I need to draw the symmetrical picture. I want a central 96% for my confidence interval. So if that's 96%, I've got 2% hanging off each end. So what value should I look up on inverse normal? Well, the picture is always a value with the probability to the left of it. So if I combine the 96% and the 2%, this is a probability of 0.98. So on my calculator, I need to go into distribution 7. I need inverse normal. I enter an area of 0.98. I get a z value of 2.0537. So z equals 2.0537. And now all I've got to do is put these values into the recipe. So I need to do 251.1 plus or minus 2.0537 times 1.94 over the square root of 50. So if I put all of that into my calculator, okay, 251.1. Okay, let's do the lower limit first. That's going to be minus 2.0537 times 1.94 divided by the square root of 50. Okay, enter that, and I get 250.536. So that's 250.54. Okay, probably don't need this number of decimal places, but let's not take any risks. I can always round later. And for the upper limit, that was exactly the same thing, but with a plus there. So that's going to give me 251.66. Now when they're quite close together, you can see that actually having the extra significant figures helps. I wouldn't actually round this one to 3 significant figures because I'm going to be going to the nearest whole number. So I might even leave my answer like that. So, oh no, it says give the limits to 1 decimal place, so I need to do what I'm told. So that's 250.5 to 251.7. So there's my confidence interval for B1. Okay, and now I've got to comment on the manufacturer's claim. So the manufacturer is claiming that the real mean, the true mean of the distribution, is more than 250 grams. And my confidence interval actually only contains values. The bottom of my confidence interval is 250. So I'm going to say all values in the confidence interval are greater than 250. So I can't be completely sure, but if I'm 96% confident the mean's in here, and all of those values make the manufacturer's claim true, I think I can say, so the claim is likely to be true. And I'm done.